Welcome back to our second segment. Now we focus our attention on, the real life, applications of electrostatics, and remember, in science, we so much talk about predictions, quite a lot to say, okay, what would happen if you take a balloon, and rub it on your jersey, woolen jersey, already we are thinking the science behind that demonstration to say, okay, there is friction while the two surfaces are actually in contact. So there's a force that, the balloon exerts on the jersey, and while that is happening, our focus or our concern or what is of interest to us is exactly what happens to the charges, while they come into contact, charges will actually be transferred. Now let's look at a scenario where you rub a balloon on a woolen jersey. Take note of the material. A balloon is rubber, okay? This is rubber, right? Okay, and then a woolen jersey, it's a different material altogether. But both of them are actually, different types of material. And so one of the two is actually an electrical conductor. So rubber is an insulator, right? So the rubber is an insulator, all right? And then the woolen jersey is actually an electrical conductor, all right? So if these two are actually rubbed against each other, we've got a scenario here that I just want us to look at. Okay, here's a typical example of a balloon, okay? Now, what is happening? The balloon is neutral. Now, let's break it down. When a material is neutral, does it necessarily mean that it doesn't have any charges? Definitely not. It says the number of positive charges equals the number of negative charges. Hence, the net charge is equals to 0. Okay? So neutral materials do retain charge. However, the amount of charges, positive versus negative, is equal. Hence, the net charge is equals to 0. That's the most important thing. Now, if you look at the balloon in itself, the number of positive charges in this simulation of the balloon, it is the same as that of the positive charges. The similar thing can happen with your woolen jersey, right? So the woolen jersey has got a lot of atoms, millions and millions of them. Now, the number of positives, again, is equals to number of negatives. So what happens if we rub these two against each other? Just look at that, okay? Look at the changes that have happened, and look at, observe the force that the jersey exerts on the balloon and vice versa. Now, if we pull this balloon away and try to analyze it, there are some observations that we've definitely made there. You'd realize that now there are many negative charges on the surface of the balloon than it initially was. So what that says to us is that the insulator, sorry, the conducting material, which is the jersey, had, some of its negative charges transferred to the balloon. Now, you can immediately predict that, oh, okay, now the balloon has more negative charges than positive, meaning that the net charge on the balloon is actually negative, while the opposite is true for the jersey. On the surface of the jersey, closer to the balloon, you'll see that there is a cloud of, positive charges. Now, yes, charge, if they come into contact, the transfer does okay. But if we bring them closer, what exactly happens? We still have more and more charges getting to the balloon, and you can immediately, if we pull it away, naturally, this balloon will move towards the jersey, as you can see. It's magic, but yes, it's the science which explains how charges or charged materials interact with each other. Now, beyond just the transfer of charges, you also need to recognize and appreciate the fact that, there are electrostatic forces that exist between the balloon and the jersey. Now, the force exerted by the balloon on the jersey, because on this side, they're actually positive and negative, which is oppositely charged. There's an attractive force, which explains then our everyday life observation. You take off your jersey, you are rubbing the jersey against your body on a hot summer day. You observe some sound, some sparks. So that's static electricity. It's a perfect example of exactly what happens when two materials are rubbed against each other and charge is transferred between the two of them. But what is also particular interest to us is the nature of charge that arises due to friction while you rub them, as well as how these charges end up interacting with each other. What we already know is that positive and positive, they repel, while positive and negative, they attract, which is the case with the balloon and the jersey. So that's quite an interesting observation. Right, moving along, right, we would also want to look at a scenario whereby the very same balloon and jersey is actually between two materials. That's your wall over there, as well as that's your jersey. But now we've resetted everything. Let's go back to the simulation and talk to it a little bit. Right, now I'm gonna reset everything, but now you'd realize that we've got a wall. Okay, the wall is also neutral, right? Because in parties, balloons are a very common feature, and some of these demonstrations, I think they'll bring an understanding of, you know, the science behind, you know, the everyday life observations that we make. So if we take the balloon to the wall, you'll realize that there's not much happening there. Why? Because both of them are actually neutral, and both of them are actually insulators. Now, the charge cannot be transferred between those two. However, if we do the opposite, you go to the jersey, that there is that observation. Now, look at what happens. Now the balloon can stick onto the wall, okay, because it has acquired excess negative charge. It means it has got more negative charges than positive charges. Hence, the net charge in it is actually negative, right? Okay? So that was the simulation. So the science actually behind the everyday life observation is what is of interest to us today, to say there is some thinking as to why we see or why we observe what we do in everyday life. It's static charges, you know, interacting with each other in real life or in space. All right, okay? Right, then another prediction. When you bring a charge comb, okay, you can try this at home. You are free to do that. You can bring a charge comb. Now the comb is charged already. Now let's unpack the charging of the comb. Ask yourself the important question: how do you charge a material? It's either you rub it against your hair, or you rub it against your jersey, or whatever material. What will happen is that this material will either acquire excess charges or have more negative charges or more electrons than protons, or it will lose electrons. Whichever way, it becomes charged. Whether it's positive or negative, it's a material for now, right? So if the comb is charged, and then we bring it closer to a stream of water. This is the demonstration that I'm talking about. You'd have observed this maybe at home. You'd realize that the stream of water bends. Now, what does that say to us is that there is a force that exists between the comb and the water. Water in its very nature, it's polar. We've spoken about polarized. It means the water molecules, the water molecule actually has a side which is positive and a side which is negative, right? Something like that. So what that simply means, water is polarized. Yes, it's neutral, but the distribution of the charges in the water molecule is such that one side of it is positive and one side is negative. So when you bring a charged comb, let's say this comb is positively charged, what will happen? The negative side of the water will actually be attracted to the comb. This is one classic example of how charges interact with each other. It still goes back again to say that like will repel and opposite will actually attract, right? Okay, and then how can you detect if something is charged or neutral? There is a piece of apparatus in science that we refer to as a gold leaf electroscope. So what it does, it actually demonstrates the interaction of different types of charge, positive and positive, repelling each other. The similar thing happens with like charges which are negative, while the opposite, which is the positive and the negative, actually exert a force of attraction on each other, right? Okay, so here is a scenario. So say for argument's sake, we've got a material that is charged. This is negatively charged. The electroscope is neutral. Let's put it out there to say that if this is the, the simplest grammatic representation of what an electroscope it looks like. Okay, so if we bring this closer to the neutral electroscope without touching, polarization does occur. Okay, right? There is polarization. Remember, if we don't make contact, the field forces or the non-contact forces actually act on these charges, and polarization is due to non-contact forces. All right. Okay. So non-contact, it means the two materials must not be in contact with each other for them to actually exert a force on each other. Okay. So if we bring this, what is going to happen? The positive will actually be repelled, which brings us to repelling the negatives have been repelled because the material in itself is negatively charged. So once that happens, if we polarize the negative by repulsion without even making contact with that part of the electroscope, these two leaves will actually deflate because both of them will be more negative. So what do we know about negative charges? They experience a force of repulsion. Hence, we say that the leaves will deflate. Okay. Similarly, if this was, let's say for argument's sake, positive, what would mean? It will also polarize the positive charge by reflection, by repulsion, and then what happens is a similar observation will be made because this will be more positive. So in other words, we are saying that the interaction of charges is in nature is actually twofold. Well, it will depend on the nature of charges under consideration. If these two charges are alike, then we are saying that a repulsive force will exist between them, while if they're opposite or unlike, an attractive force will exist between them. So that's the gist of our discussion. Having said that, I think we'll take a short breather and then we'll look at quantization of charge. Exactly what do we mean when we say that charge is quantized? Let's take a short breather for now.